Okay, Wildcats. Today we're looking at Tuesday, April 16th, Half-Life Part 1 on page 59. If you would, update your table of contents. Okay, now your table of contents are updated. Let's take a look at page 59, Half-Life Part 1. All right, complete the table below and answer the following questions. Okay, so here you can see that when half-life is 0, you have 1 mass of the original Wildcat in 1883, and the number of minutes is 0. Now, after one half-life, you have half of that after 22 minutes. And in two half-lives, you have 1/4 after 44 minutes. So as you can see the pattern, we're dividing by 2 here, so 1/4 divided by 2 is 1/8. And we're doubling the minutes, so 22 minutes, 44 minutes, 88 minutes. Okay, so in 4 half-lives, there's 1/16 left of the Wildcat Tinium. And we're going to double 88, which is 176 minutes. And then on the 5th half-life, that's 1/32 of Wildcat Tinium 1883. And we double 176, which is 352 minutes. Okay, then we have 1/64 Wildcat Tinium 1883 in 704 minutes. And 1/28, so 1,408 minutes. And then 1 All right, so now we've completed the table. Let's take a look at the questions. Okay, based on the table above, what is the half-life of Wildcat Tinium 1883 in minutes? So the half-life, you can see in minutes, in one half-life is 22 minutes. Okay, now it says after how many minutes will there be 1 divided by 1,024 of the original Wildcat Tinium 1883 remaining? Well, it's after 11,246 minutes. And the half-lives would be 10. All right, go ahead and finish up problems number 2 and 3. All right, now this page is going to be in your journal on page 59. And so will this page be in your journal on page 59, okay? Now it says using the half-life you found in number 2 and the formula 0.5 e to the kt, where t is the half-life in minutes, find the decay constant k of the Wildcat Tinium 1883. So we have 0.5 equals e to the k, which we don't know, times t, which is 22 minutes. Okay, so to find k, what we're going to do is we're going to graph the left side and the right side. Okay, and let me adjust the camera here. There we go. It's probably going to be as good as we're going to get. New document, on, new document. If I can get this to work, new document, add graph. So we're going to graph 0.5 enter. Tab, to get E, it is, and that's way too bright. There we go. It's probably as good as we're going to get. To get E, E is right here. Okay, so E to the, now we can't use K when we're graphing, we're going to use X. So X times 22, enter. Now you can see that these intersect. So the intersection point will give us the K value. Okay, so we're going to go to Menu, Analyze Graph, and we want intersection. We're going to move the cursor to the left, click, and then you're going to slide until it says intersection, click again. Now it's hard to see, so I'm going to move the hand over the cursor, control click, I'm going to grab and bring it down, press escape. And I know it might be a little hard to see, so I'm going to write it down so you can see it, but the K value is here, which is negative 0.032. Okay. All right, so now let's take a look at number 5. The bones of a wildcat in an archaeological site contain 30% of the wildcat tanium as a living sample of the animal. Use the formula P equals EKT, where P is a percent of the wildcat tanium, 1883 left, and the K value found in number 4 to estimate how long ago the animal died. So P would be point, and I guess we can do our work here. So 0.30 equals E. Let's focus on a little bit. E to the K value, which is negative 0.032 times, now, T. It's an ugly T, but it's a T nonetheless. All right. So we're going to do the same thing we did before. So we're going to go to All New Document, No. And let me see if I can fix the camera a little bit. That seems to work. Let me brighten that calculator. It's about, again, as good as we're going to get. So we're going to go to Add Graph. So 0.30, enter. Tab. Now we're going to graph E to the negative 0.032 times. Now we're going to use X instead of T. Press enter. Now we can't see the intersection point, so we're going to go to Menu, Window Zoom, zoom out, click once, twice, probably 3 times, press escape. You can see that at some point here they're intersecting. So I'm going to go to Menu, Analyze Graph. We want the intersection. Click, move the cursor over here, click, and then slide until it says the word intersection. Press click, and I'm going to move my cursor over here, control click, bring it down, press escape. You can see here that the wildcat died 37.6 years ago. All right, now we're not using the calculator. Let me see if we can brighten the screen up. All right, so now let's move on to number 6. All right, in the following table, convert the half-lives from scientific to standard notation. So here, when it's 10 to the 3, you move the decimal place 3 places to the right. So 5.7, you move 1, 2, 3, and you fill in zeros here. So that's 5,700. Okay. Now here, Now, negative, you go left. So you go left 1, 2. So put the 0 there, decimals there. So that's equal to 0.022. Now, positive, you go to the right. So 7.0. So the eighth is that's 1, 2, 3, 4, 5, 6, 7, 8. Now let's count 1, 2, 3, 4, 5, 6, 7, 8. Fill those loops in with zeros. So that's 1, 2, 3, 4, 5, 6, 7, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And let's count. Okay. So here times 10 to the 10th, we're going to the right 10 times. So probably need to write this right here. So I have room. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you just count the zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 zeros and a 9. So 4, 9. And then 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Okay. Now, negative, you go left 5. So 1, 2, 3, 4, 5. So that's 0. Count zeros. 1, 2, 3, 4 zeros. So 1, 2, 3, 4. Okay, go ahead and finish up number 6. All right, number 7. The atomic bomb Little Boy contained about 64 kilograms of uranium-235. If this uranium had been left sitting around since 1945, use the formula A equals P parentheses 0.5 T divided by H to estimate how much uranium-235 would have decayed into thorium-231 by the year 2020. So, first we need to figure out what everything is. So, A is what we're looking for. P is 64. Okay. T we find by doing 2020 minus 1945, which is 75. And then your H half-life is here, 7, comma, comma. So you can see 700 million years. Okay. So now we substitute all this information into the equation. So that's A equals P, which is 64, parentheses 0.5 to the time, which is 75, divided by 700 million. Okay, so at that point, we're going to plug that into the calculator. And let me darken the screen a little, darken the screen a little bit. And let's plug it in. So 64 parentheses 0.5 raised to control divide 75 divided by 7, 1, 2, 1, 2, 3, 1, 2, 3 is in essence 64. And the reason why that is is because since it takes 700 million years for half of it to turn to thorium, 75 years is nothing compared, basically nowhere near that. So in essence, almost none of it has decayed. Okay. All right. Now let's leave it at dark because I think we need to calculate number 8 as well. All right. The last nuclear weapons test took place 27 years ago at Nevada test site. It was the 1030th experiment, the most conducted by any country since the first U.S. atom bomb was exploded in 1945. A sample of uranium-235 taken from the 1992 bomb test site was 0.01 grams of uranium-235 in it. How much uranium-235 was initially at the site? So we're using the similar equation, but here we know how much is left. So that's 0.01. We don't know how much was originally there. All right, so we're going to simplify this first, and so let's do that, okay? So in our calculator, we're going to put parentheses 0.5 to the control divide 75 divided by 700 million. Press enter. So that's 1. So 0.01 equals 1p. So basically you have 0.01 grams of uranium. And again, the reason why the number is the same is because it takes 700 million years for half of that to turn into thorium. Okay? All right, so with that, if you would, go ahead and finish up your examples. And then I believe you're done for the day unless you want to start on tomorrow's Half-Life Part 2. Again, have a wonderful Wildcat